Morning. Today we'll talk about sections 4.3. So section 4.3, it's about first derivative and second derivative tests. So we'll look at that in just a second. Okay, so here we go. So 4.3. So how derivative affect the shape of a graph? So we're going to be doing the increasing or the decreasing test first. So here's the definition for increasing or decreasing test. If f prime of x is greater than zeros on the interval, then f is increasing on that interval. And then for part B, so if f prime of x is less than zero, so that means the velocity is less than zeros on the interval, then that means f is decreasing on that interval. And here's the definition of the first derivative test. Suppose that c is a critical number of a continuous function f. So if f prime changes from positive to negative at c, so then f has a local maximum at c. So what this one is saying is that if the function is considered increasing and then decreasing, then you'll see the local max. Okay, so let me show you the graph for this one. Okay, let's see. So let's say we do have a curve. So started with increasing curve, and then all of a sudden it's decreasing. So that means at point C right here, so that would shows you the local maximum. Okay, so the local maximum. Okay, so let's say that if f prime changes from negative to positive at c. So what that tells you for the original function is that started with decreasing and then increasing. So that means at this point the value of c right here. So that means f has a local minimum at the value of c. If f prime does not change sign at c, then f has no local maximum or minimum at the value of c. So let's say that just keep increasing. So as c right here, it's not the max or the min, or this one is just like decreasing. So for the value of c right here, so there's no max or min. Okay. So now let's take a look at that one of the example. So find the interval on which f is increasing or decreasing, and then find the local maximum and the minimum value of f. Okay, so this one I probably need more space here, so let me just write this problem down first, and then I'll show you that on the next slide. So give me 1 sec. So I need to transfer this one to the next slide here. So we do have f of x. So that one it's a cubic trinomial. So that one is 4x to the power of 3 plus 3x squared, and then minus 36x, okay? So we're going to put into the next slide for this one here, because I need more space. Okay, let's see. New slide. Okay, so for this one, f of x. So we do have 4x to the power of 3, and then plus 3x squared, and then minus 36x. So first thing that you want to do, you want to find the first derivative. So once you get the first derivative, you'll get the, well, you can find the local max or the local min. So 4x to the power of 3, derivative of this would be 12x squared. And then 3x squared, derivative of 3x squared, then that'll be 6x. Derivative of negative 36x, then that'll be minus 36. So now, in order to find out the critical number, we set it equal to 0. So before we solve for 0, let's take out the greatest common factor. That's always the first thing you always want to factor out first. So 12, 6, and 36. Obviously 6, that's what they share in common. So we left with 2x squared plus x minus 1. And then from here, you want to factor the trinomials. So 6, bring it down. So we got 2x, 1x. So this one we need x plus 1 here, and then 2x minus 1 here. Okay, so you just want to factor it. And set equal to 0, so let's find out the critical number. So we do have x equals 1/2, and then x equals negative 1. So now, once you're doing this, so 1/2 and negative 1, well, those are the critical number. Again, let's just, so critical number. So we just need to find out the increasing, decreasing interval, and also we need to determine whether that is a max, the local max, or the local min. So from least to the greatest, -1, 1/2. And we do know that f of x is a continuous function from -infinity to infinity. So this one from -infinity to infinity. So this one is called the f prime of x, the first derivative line test, okay? So the first derivative line test. So basically we just need to plug in a number, run between -infinity to -1, -1 to 1/2, 1/2 to infinity. So let's select any number here, any number from -infinity to -1. So I'll pick -2. So number run between -1 and 1/2, so I would like to choose 0, easy number. And then 1/2 to infinity, I would like to select 1. So now let's plug in the number to the first derivative and see what that is. So we do have two factor here, well, +6. We can just put it in right here, or we can just ignore that. So we do have 2x minus 1, x plus 1 for the factors. And then the resulting factor, make sure that got to be either positive or negative. So now let's plug in -2. So 2 times -2, then that'll give you -4 minus 1, so it's negative. So -2 plus 1, so -1, so negative. Negative times negative, positive. So now, if the first derivative, going back to the definition, if the first derivative is positive, so what that implies is that the original functions must be considered increasing. So let's put the arrows up like that. And then for the next interval, so we just want to go through the same process. So since we select 0, so we plug in 0 to the factor. So we got 2 times 0 minus 1, so it's -1, negative. So 0 plus 1, positive, so negative times positive, which is negative. So derivative is negative, so that means the original function is going to be considered decreasing. Okay, so this one is just an indicator. And now the next one, so we just started with 1. So let's plug in 1 here. So 2 times 1 minus 1, so positive. 2 minus 1, so it's positive. And then 1 plus 1, positive. So positive times positive, positive. So that means the original function is going to be considered increasing. So now, we do know that -1, so this one is increasing and then decreasing. So increasing and decreasing. So that means at -1, so this one will show you the local max. And then 0, 1, so this one is decreasing and then increasing. So that means at 1/2, so you'll see the local min. Okay, so now let's go back to the instructions. And let's see. Find the interval in which f is increasing or decreasing. Okay, we just found them. And then find the local maximum and the minimum value of f. So basically, we're not just finding the value of c. We need to plug in a number back to the original functions to find out the exact value for y. So basically, this one, just plugging that -1 back to the original function. So we can find out the local maximum. So we got 4 times -1 quantity to the power of 3 plus 3 times -1 quantity square minus 36 times -1. Again, I'm just plugging a number back to the original function. So -1 quantity to the power of 3, then that's what? -1, -4. So -1 quantity square, positive 1 times 3, so plus 3. And then negative times negative, so positive 36. So we got 39 minus 4, which is 35. So that means for the local max, so it's -1 comma 35. And then for 1/2, again plug in a number back to the original function. So 4 times 1/2 quantity to the power of 3 plus 3 times 1/2 quantity square minus 36 times 1/2. So let's do it mentally. So let's just put it right up here. So f of 1/2. So 1/2 to the power of 3, so we got 1/8. 4 times 1/8, so we do have 1/2. And then 1/2 square, so 1/4 times 3, so 3/4. Minus 36 times 1/2, so minus 18. So common denominator, that's 4, so 2/4 plus 3/4 minus So 4 times 18. So 8 times 4, 32. 1 times 4, 4 plus 3, 72. So combine this. So 5 over 4 minus 72 over 4. So which is 67 over negative 67 over 4. Okay, so rewrite it. So 1/2 comma negative 67 over 4. And that will give you the local minimum. Again, in order to describe the increasing, decreasing interval, you can just rewrite this one in a short statement. Okay, so from negative infinity to negative 1, so f of x is considered increasing. And also from 1/2 to infinity, so f of x is also increasing. But from negative 1 to 1/2, so f of x is decreasing. Okay, so now let's try another example like this. So for the next one, we do have sine of x plus cosine of x from 0 to 2 pi. Okay, so let's do that one. So it looks like this one is considered one full period, one full cycle. Okay, again, I need the new slide for this. So for part B, we do have f of x. So sine of x plus cosine of x. And this one, it goes from, well, x goes from 0 to 2 pi. So just want to make sure that I transfer the problem correctly. Yeah, it is. Less than or equal to, less than or equal to. Okay, so again, same process. So first thing that you want to do, find the first derivative. So that's the first step. So derivative of sine of x, cosine of x. Derivative of cosine of x, negative sine x. So then the next step, you want to find out the critical number. So you want to set the derivative equal to 0. So that means cosine of x equals sine x. So when does that happen if cosine of x equals sine x? From 0 to 2 pi. So back to trig. So that's a unit circle. So that means we can find the solutions either from quadrant 1, quadrant 2, quadrant 3, quadrant 4. It's kind of like a bow tie or the butterfly. So that means x must be pi over 4. Okay, so positive, positive, so that's considered pi over 4. And also it could be in quadrant 3. Okay, quadrant 3, then that'd be 5 pi over 4. Now for those you might be wondering, how come it's not in quadrant 2 and quadrant 4? Well, in quadrant 2, cosine is negative, but sine is positive. So they're not consistent. Same thing happened in quadrant 4. So this one, it's positive, negative. Okay, let me put in the sign, negative, positive. But this one down here, it's positive, comma, negative. So that's why they're not consistent. So we cannot include the quadrant 2 and quadrant 4 solution. It's only quadrant 1 and quadrant 3. Okay, so now, once we find a critical number, okay, so this one is just the critical number. And now we're going to do the line test, the first derivative line test. Okay, so let's set up the straight line. Again, this one is about finding the number, and then you want to plug in the number back to the first derivative. So it's not going from negative infinity to infinity, obviously, so this one, it's considered the endpoint. So from 0 to 2 pi. And the critical number that we find out, so this one is pi over 4. And also we do have 5 pi over 4. And now let's figure out the number so we can verify that in the interval. So anything that's less than pi over 4, so we can test something like pi over 6. Okay, any number right between pi over 4, 5 pi over 4, so we can test something such as pi. Any number from 5 pi over 4 to 2 pi, so we can test 3 pi over 2. Again, we want to plug in a number back to the first derivative. So we do have cosine of x minus sine of x. Okay, so let's plug in a number back here. Cosine of x minus sine of x. So cosine of pi over 6. So cosine of 30, that's root 3 over 2. So sine of pi over 6, that's 1/2. So root 3 over 2, it's actually greater than 1/2. Okay, so that means it's going to be positive. And then pi over 4, 5 pi over 4, we pick pi. So cosine of pi, that's negative 1. Sine of pi, that's nothing. So negative 1, so which is negative. And then 3 pi over 2, cosine of 3 pi over 2, that's nothing. Sine of 3 pi over 2, that's negative 1. But don't forget, it's minus negative 1, so it's positive. So again, if the sign changes shows positive, negative, so that means the original functions. So we can find out whether that's considered increasing or decreasing. Okay, so let me fix that one. So this one's supposed to be f of x. So if the first derivative is positive, that means for f of x it must be considered increasing. F prime of x is negative, so that means the original function would be considered decreasing. And then f prime of x, once again positive, so that means the original function, f of x, must be increasing. Okay, so that means for the increasing interval, so we do have the number from 0 to pi over 4, union, and then 5 pi over 4 to 2 pi. And then for the decreasing interval, so we do have the number from pi over 4, and then all the way through 5 pi over 4. Okay, so this one is about the increasing, decreasing intervals for doing the first derivative line test. And now, what about for the local max and the local min? So as you can see that here, so this one is increasing, decreasing, so that means at pi over 4, so guarantee that there's a local max. And then from here, decreasing, and then increasing, so that at 5 pi over 4, there's a local min. And also you need to plug in a number back here to find out exactly what y is. So f of pi over 4. So sine of pi over 4, so we do have root 2 over 2. Cosine of pi over 4, it's also root 2 over 2. So root 2 over 2 plus root 2 over 2, then that would give you 2 root 2 over 2, which is root 2. So that means at pi over 4 comma root 2, so that guarantee it's the local max. And then plug in another critical number back to the original functions, 5 pi over 4. So sine of 5 pi over 4, then that would be negative root 2 over 2. And then cosine of 5 pi over 4, another negative root 2 over 2, so then that would be negative root 2. So that guarantee at 5 pi over 4 and negative root 2, then that would be the minimum. Okay? So now, let's move on to the next slide and see what else that we have, or back to this one. Concavity tests. Concavity, so that means you want to find out whether the curve is concave upward or downward. Okay, so let's say that we do have f double prime of x. It's greater than 0 for all x in the interval. I, that means the interval. Then the graph of f is concave upward on I. So what this one is saying, so that means if f double prime of x is greater than 0, the second derivative. Okay, let's do some annotations. If the second derivative is greater than 0, so that means f of x must be concave up. If that's concave up, that means facing upward, so that means it's a happy face parabola. And for the second part of the condition here, so f double prime of x is less than 0 for all x in I. Then the graph of f is concave downward. So if the second derivative, well, the first one is greater than 0. So this second part of this, if this one is less than 0, so what that implies is that f of x must be concave down. So if second derivative is greater than 0, so that means it's a happy face parabola. But if that's less than 0, so that means f of x must be sad face, because that's upside down. Another thing that you need to know, it's the definition of a point of inflection. So let's say that C, f of C. It's called a point of inflections on f. Well, if that happens, so that means f double prime of C must be 0. So it's kind of like the way we find a critical number, but for the critical number is by setting the first derivative equal to 0. But now in order to find out the point of inflections, the x value, so we need to set the second derivative equal to 0. Okay, so we're going to do some example like this in a minute. Okay, so on the next slide. So find the inflection points on the interval of concavity for the following functions. So this one is just asking about the point of inflection. It doesn't tell you about the interval whether that's concave up or down. Okay, so just find out the point of inflections or the inflection points. Okay, so first thing that you want to do, so for g prime of x, take the derivative. So we got 0, 24x squared, and then plus 4x to the power of 3. Now, again, inflection point, that means we need to find the second derivative. So one more time, so g double prime. So derivative of this, then we got 48x plus 12x squared. So now we want to set that equal to 0. So take out the greatest common factor, so we can pull out 12x. Greatest common factor. So we left with 4 plus x. Okay? So that means the point of inflections, we do have x equals 0, and then x equals negative 4. But don't forget, you need to plug in a number back to the original equation. So for 0, so g of 0. So it looks like that one is going to be 200. Oops. So g of 0, so then that'll be 200. Okay? So that's one of those point of inflection. And then negative 4, so plug in a number back here. So negative 4 to the power of 3, so then we do have negative 64. Well, this one you can find out. Okay, let's do it up here. So g of negative 4. So it's 8 times negative 64. And then negative 4 to the power of 4. Okay, so just find out what that is. So that will give you the value of another point of inflection, the y value. So that means at negative 4 comma, whatever that number is. So that will give you the another point of inflection. Okay, so now let's try the next one. So the next one is quite similar. So let's see. Let me erase what I just did here. Clear annotation. Here you go. So the next one, this one looks like it's a combinations of linear and radical. It's a product of linear and radical. So this one you probably want to use the product rule. Okay, so let me just use the blank slide for this. So just have more space. So a of x. Okay, so let's see. So what we got for this one here, so a of x. So that's x times the quantity of x plus 3 to the power of 1/2. Now, there's no way we can expand this out because this one, it's not a perfect integer. It's a rational number. So the thing that we can do, we can use the product rule. So a prime of x. So derivative of x, which is 1. Okay, so that's 1 times the second functions, the radical function. And then plus the derivative of the second function. So it's 1/2 times x plus 3 to the power of negative 1/2 times the first function, which is x. So that would give you the first derivative. And for those you might be wondering, can I simplify this a little bit before taking the second derivative? So for this one, I strongly recommend you to take the second derivative first before you factor it, because you want to find the point of inflection. So this one is just 1 times this, so that means using the power rule. So 1/2 times x plus 3 to the power of negative 1/2. And then looks like this part right here, we need to use the product rule again. So plus 1/2 times negative 1/2, then that'll be negative 1/4 x plus 3 to the power of negative 3/2 times x. And then plus derivative of x, so that's 1 times 1/2 x plus 3 to the power of negative 1/2. So now you might be wondering, it's a little bit complicated. It is, because there's so many things involved right here. So now another thing that you can consider doing, you can combine the like terms. Okay, so the first term and the last term. So basically they're exactly the same thing. So it's 1/2, 1/2. So we can combine them together. So then that'll be x plus 3 to the power of negative 1/2. Because 1/2 plus 1/2, that's just 1. But don't forget, bring down the negative 1/4 quantity x plus 3 to the power of negative 3/2. Okay, so I just need the eraser here. So minus 1/4 x plus 3 to the power of negative 3/2. So again, we want to find out the point of the point of inflection. So we set it equal to 0. So we took out the greatest common factor. So the greatest common factor we have is x plus 3 to the power of negative 3/2. And now you might be wondering what's left here, since we took out negative 3/2, but this one is supposed to be negative 1/2. So that means it's just left with x plus 3 to the first power. Because 1 plus negative 3/2, then that'll give you negative 1/2. And then minus 1/4. Now we do know that this one is going to be going down to the denominator, so we cannot set that equal to 0. So the only thing that we can set equal to 0 is just x plus 3 minus 1/4 equal that set equal to 0, because that goes on the numerator. So we do have x, 3 minus 1/4, so 3 minus 1/4, we do have, okay, so 12 over 4 minus 1/4, so that's positive 11 over 4. And then x, so then that'll be considered negative 11 over 4. So that's the x value for the point of inflection. And then whatever that you have for the x value, so you want to plug in back to the original function to find out what y is. So a of negative 11 over 4, so that equals negative 11 over 4, times the quantity of negative 11 over 4 plus 3 to the power of 1/2. So this one is just like 12 over 4, so it's 1/4 to the power of 1/2. So this one is just square root of 1/4, which is 1/2. So negative 11 over 4 times 1/2, and that'll give you negative 11 over 8. Okay, so for that part right there, so for a of negative 11 over 4, so then that would give you negative 11 over 8. So that's the point of inflection. Okay, so now let's see what else that we have for the rest of this. So for the next part is the second derivative test. So this one is quite similar to the first derivative, but one thing that you need to find out is the second derivative. So suppose that f is continuous near c. So if f prime of c equals 0, so that means showing c is the critical number. And also shows that f double prime of c is greater than 0. So that means f has a local minimum as c. So what this one is saying that for the second derivative, if that's greater than 0, so that means it's concave up. So at the value of c, so it shows that it's a local minimum here. And then for the other part, if f prime of c equals 0, so it shows that c is the critical number. But f double prime of c is less than 0, so that means it's concave downward. And then point C here, so that it's going to show this point here, it's the local maximum. Okay, again, second derivative, what does that imply? The concavity. Okay, so we're going to be doing some example. Well, you see some of the example like this from the practice part of the homework that you're doing. And let's see any practice similar to this one. Okay, this one is just find the concavity and also the inflection point. Okay, let me fix the spelling here. So this one, inflections. Okay, so one problem at a time. Okay, so let's start it off with part A. So let's find out the first derivative. So h prime of x. So we do have 5 times the quantity of x plus 1 to the power of 4. Okay, give me one sec. This one, pen, it's not working nicely. Okay, here we go. Minus 5. And then derivative of a constant, that's 0, so no need to worry about that. And then h double prime of x. Okay, by the way, this one is h prime of x. Sorry about the handwriting, so the pen, sometimes it's not that stable. So second derivative, so we do have 20 times x plus 1 to the power of 3. So what I'm doing here is just using the power rule again, along with the coefficient rule. So we want to set that equal to 0, so obviously x must be negative 1. And then you want to find out about the concavity. So this time, instead of doing the first derivative line test, we're doing the second derivative line test. Okay, because we want to find out about the concavity. So negative 1, that's right here in the middle. We do know that the original function is a polynomial, so that means it runs through all the way from negative infinity to infinity. So let's pick any number. So let's say negative 2, and then over here, 0. So we plug in a number to the second derivative. So we got 20 x plus 1 to the power of 3. Let's find out what the result is. So negative 2 plus 1, then that's negative 1. Negative 1 to the power of 3, negative. Negative times positive, negative. So this one is negative. And then 0, so 0 plus 1, so everything's positive, so it's positive. So again, if the second derivative is negative, so that means it shows the concavity. This one is concave down. So from negative infinity to negative 1, so it's concave down. And then from negative 1 to positive infinity, so that means for f of x, it's considered concave up. Okay? So that's the implicity. And now let's see what else that we have for the instruction here. Find out the point of inflection. So negative 2, 0, those are the point we test. But for the number, the value that we find out for the x value of the inflection point, it's negative 1. So we need to plug in a number back to the original function, back to here. So we got negative 1 plus 1, 0. So negative 5 times negative 1, positive 5, minus 2, so it's 3. So again, plug in a number back to the original equation. So we got negative 5 times negative 1 minus 2. Well, this one got canceled, so that's why there's no need to show the work for that part. So it's 5 minus 2, then that'll give you 3. So negative 1 comma 3. So that's the point of inflection. Okay, so now let's try the next one. So the next one is quite similar. It's a trig function. Okay, so let's use different color for this one. Okay, let's use blue. F prime of t, so we do have 1 plus negative sine t. Again, this one is just the first derivative. And then f double prime of t. So that would be 0. Derivative of negative sine t, then that would be negative cosine t. Now don't forget, you need to set it equal to 0. Now I've got to be careful with the interval here. So this one will run through from negative 2 pi to positive 2 pi. So negative 2 pi to positive 2 pi. So basically this one is going this way. So negative pi, negative 2 pi started from here all the way to 2 pi. So that means we need to go around 2 cycle. Well, actually it's a 4 cycle. Okay, so let's see what are the solution here. So for cosine of t equals 0, so that means it could be what? Negative pi over 2, positive pi over 2, and also it could be, well, go around the circle again. So then that would be considered 3 pi over 2. And also up here, negative 3 pi over 2. Okay, let's see. Anything else that's missing here? Okay, so you would just go around. Add 2 pi again. So add 2 pi again. So you got 4 pi over 2. Then that would be 7 pi over 2. No, I think that's it. Pi over 2, negative pi over 2, 3 pi over 2, negative 3 pi over 2. And then after that, you want to do the line test. Okay, so negative 2 pi. Again, this one shows the endpoint. Positive 2 pi. So we got negative 3 pi over 2 over here. So we do have negative pi over 2. And then positive pi over 2. So I need one more interval here. Okay, let's just fix this one. So the next position would be consider 3 pi over 2. Then 2 pi. Okay, so basically just plugging a number here. So negative pi, 2 pi, negative 3 pi over 2. So things I can use for the interval, we can use negative pi. Negative 3 pi over 2 to negative pi over 2. So for that one, let's see here in a second. So negative pi is supposed to be the next interval. So just plug in a number and test it and find out exactly, what the signs are, whether that's positive or negative. So we do have 1, 2, 3, 4, 5 intervals, so need to be tested. So from negative 3 pi over 2 to negative pi over 2, so we can test negative pi right here. Okay, so anything that it's considered negative 2 pi to negative 3 pi over 2. Okay, wait. Okay, negative 2 pi. So this one, you can put in any number. Okay, perhaps maybe negative 5 pi over 4. Okay, over here, negative pi over 2 to pi over 4, 0. Pi over 4 to 3 pi over 2. Then that would be pi over 2. And then 3 pi over 2 to 2 pi. So we can put in 7 pi over 4. Well, actually, this part right here, you want to put in negative 7 pi over 4. Yep. So for that one, negative 7 pi over 4. Okay, so plugging a number back to the second derivative. So cosine of negative 7 pi over 4. Okay, so, and that one, it's going to be considered negative. So that means it's going to be concave down right here. And then negative pi, cosine of negative pi. Well, we do know that cosine of pi would be considered negative 1. So cosine of negative pi, it's also negative. Well, let's see. Negative, but negative times negative. positive. Okay, so this one's going to be positive. Okay, and then cosine of 0. Cosine of 0, that's 1, so negative. So this one's back to negative. So here's concave up, concave down. And then pi over 2. So cosine of pi over 2, which is 0. This one, let's see, pi over 2. Oh, you know what? Pi over 2 is supposed to be one of the number here. We cannot use pi over 2. I make another error here. So this one's supposed to be pi over 2, not pi over 4. So for that one, we want to use... okay, so over here, we want to test the number with 3 pi over 4. So cosine of 3 pi over 4, then that's negative. Negative times negative, so going back to positive. So as you can see that here, so the sign is just like alternating. So let's say that this first one you started with negative. That means the next interval is going to be positive. Well, is that always true? Well, for many cases, it's always like that. The sign is always being alternated. So this one, that means concave up. And then 7 pi over 4. So cosine of 7 pi over 4. So quadrant 4 here. So it's going to be positive. But positive times negative, then that'd be negative. Yep, so that makes sense. Okay, so that shows the interval, the concavity. Again, in order to find out the y value for the point of inflection, so you need to plug in those number. Negative 3 pi over 2, negative pi over 2, positive pi over 2, 3 pi over 2. Back to the original equation. Okay. So now let's just stop the video here today. So this one is just the first half of the lecture notes for section 4.3. So for the next video, I'm going to put up the one for the second half. Okay. So just get started with the homework for 4.3 first and see any problem that you come up with. Okay. So thank you for watching the video today, and I'll see you guys next time.